Is there anything you'd like to add, Sinan, Kemal, before we start, or is there any questions before we start?
I think we can start.
Okay. Let me share the video.
Maybe we can state that we will be playing pre-recorded videos because we had some technical issues in previously organized workshops and tutorials. So I think it's best if we, recorded our talks and just play them. Then we will have Q&A after each part. So we will have 3 parts for our tutorial. And after each part, we will have some Q&A. At the end of all parts, we will have one Q&A session as well. Thank you.
All right, thank you. So let's start.
Hello everyone, welcome to our CVPR 2022 tutorial on performance measures in visual detection and their optimization. We are 3 researchers from the Department of Computer Engineering, Middle East Technical University. My name is Emre Akbaş and I will be giving the first part of the tutorial. My colleagues Sinan Kalkan and Kemal Öksüz will be delivering the second and third parts of the tutorial. Before starting the first part, let's take a brief overview. Our tutorial is intended for researchers and practitioners who are working on visual detection problems. By visual detection, we particularly mean the following 4 problems: object detection, instance segmentation, key point detection, and panoptic segmentation. This tutorial is especially for you if you are particularly interested in the evaluation of visual detectors or curious about the limitations of commonly used performance measures, or if you have been thinking about how we can unify the training and evaluation of visual detectors. This tutorial is intended for you. Our tutorial consists of 3 main parts. The first part will give us the background and basics on evaluating visual detectors. We will introduce the visual detection problems and describe the widely used performance measures as well as the recent advances in this subject. In this part, we will basically be explaining average precision, the most widely used performance measure, and briefly talk about its limitations. Then we will introduce the panoptic quality and the localization precision recall error metric. Finally, we will close by introducing more recent progress in the field, namely AP variants such as AP fixed and AP pool, probabilistic detection quality, boundary intersection over union, and optimal correction cost. In the second part, we will present an analysis of the performance measures that we introduced in the first part. We base this analysis on 3 desirable properties to find in a performance measure, which are completeness, interpretability, and practicality. We will have a closer look on average precision, panoptic quality, and localization recall precision error. We will present analysis of these measures in terms of completeness, interpretability, and practicality. In the final part, we will talk about the optimization of performance measures. We will draw your attention to an often overlooked fact, which is the discrepancy between the training objective and evaluation measure in visual detection. A typical example of this discrepancy would be an object detector which uses some sort of cross-entropy loss and L1 loss as training objectives, but its performance is evaluated by average precision. These objectives are obviously not the same. We are going to talk about recent efforts that try to close this gap, all of which are based on ranking-based loss functions. So we will introduce these ranking-based loss functions, which are actually not differentiable, but we will introduce a method called the identity update, which gives us a gradient to minimize these non-differentiable ranking-based loss functions. We will give 3 examples of such loss functions. These are average precision loss, ALRP loss, and finally rank and sort losses. We hope that you find our tutorial useful. Okay, after this overview, let's start the first part of the tutorial, the basics of evaluating visual detectors. Let us look at a more detailed table of contents for this part. We will start by introducing visual detection tasks and talk about how the performance is evaluated in these tasks and why it is important. Commonly used performance measures will follow. We will describe how average precision is computed and briefly talk about its limitations. An in-depth analysis of AP will be given in the second part of the tutorial. After AP, we will present panoptic quality and localization recall precision. Finally, more recent advancements in this subject will follow. These are the AP variants, namely AP fixed and AP pool. Then we will go over probabilistic detection quality, boundary intersection over union, and optimal correction cost. So let us first define what visual detection is. We start with an input image and feed this to a visual detector, which is typically a deep neural network. There might be some pre-processing and post-processing steps here, but they are not shown for simplicity. The visual detector outputs a list of detections or predictions. The size of this list, N here, is arbitrary, and it depends on the content of the image and the configuration of the visual detector. Each detection in this list is associated with three elements: an object category, a confidence score, and a spatial support. The category is obviously a categorical variable which identifies the predicted class for this detection. Confidence score expresses the confidence of the prediction. It is typically a number between 0 and 1. Lastly, the spatial support describes the geometry of the region that is associated with this particular detection. The spatial support can be as simple as a rectangular box, or it can be an arbitrary shaped region. An example visual detection task is object detection. A typical output for this task would look like the detections shown here. There are two detections shown. Each has a category, which is zebra in this case, a confidence score, and a bounding box denoting the spatial support of the detected object. There are four visual detection tasks that conform to the definition we just gave: object detection, instance segmentation, key point detection, and panoptic segmentation. Object detection is the task of recognizing and locating instances of objects using bounding boxes. In key point detection, the goal is to detect important points of an object instance that characterize the pose of this object. Instance segmentation is similar to object detection in the sense that it detects individual instances of objects, but the difference is in the type of spatial support. Instance segmentation uses a dense pixel-wise labeling, and objects are marked with arbitrary shaped regions. And finally, panoptic segmentation combines instance segmentation and semantic segmentation. Individual object instances are segmented and given separate IDs, and in addition, background classes such as road, sky, building, trees, etc. are segmented. These four tasks mainly differ in the type of spatial support they use, but they can also differ in the type of confidence scores. While object detection, instance segmentation, and key point detection tasks associate a floating point confidence score with each detection, the panoptic segmentation task uses a confidence score of 1 for all of its detections. We call such detections as hard predictions. So it is desirable for a visual detection performance measure to handle all these different cases. Okay, let's now talk about what evaluation is. Remember our visual detector from a few slides back. This visual detector takes in an input image and predicts a set of detections. To evaluate these detections or to measure their quality, we need ground truth detections or annotations. These can be created by an human annotator. The list of ground truth items is again a list of arbitrary size, which depends on the content of the image. Each ground truth item G is associated with an object category and a spatial support. In ground truth items, confidence score is usually not recorded. It is automatically assumed to be 1. Now the question is, what is the amount of overlap between D and G, or how similar is D to G? This is obviously not a trivial problem, since we are essentially comparing two lists with different sizes, and the elements in each of these lists are not simple entities. They have categories, confidence scores, and spatial supports. So any evaluation or performance measure that compare lists D and G needs to compare an individual detection, for example D2, with an individual ground truth item, for example GM. And this comparison needs to account for two things: to measure the overlap between their categories, in doing so taking into account the confidence scores, and to measure the overlap between the two spatial supports. Measuring the overlap between two categorical variables is fairly straightforward. So let's look at how we can measure the overlap between two spatial supports. We will use intersection over union for this. Suppose we are comparing an individual detection DI with an individual ground truth annotation GJ. To measure the overlap between their spatial supports, in this specific example, bounding boxes, we compute the area of their intersection and divide it by the area of their union. When the two boxes are identical, we have a perfect intersection over union score of 1, and when the two boxes do not overlap at all, that is, they do not intersect, then intersection over union becomes 0. After this brief digression on localization quality, let us go back to the topic of evaluation. Evaluation in visual detection is important because it is one of the most important factors that drive progress in our field. And in some problems, maybe it is the only factor that is driving progress. Because of this, there are some desirable properties that evaluation or performance measures must have. First, evaluation must be complete. That is, given the list of detections and the list of ground truth, the evaluation should properly reflect all important aspects of performance. In the case of visual detection, these aspects are recall, precision, and localization. The evaluation measure must be interpretable. The higher its interpretability, the more insights it would give us about potential ways to improve visual detection. And finally, it should be practical. Any issue that arises during practical use of a performance measure diminishes its practicality. For example, any discrepancy between the well-defined theoretical description of the evaluation measure and its actual application in practice, or any shortcoming that limits the applicability of measure to certain cases. Now it is time to go over performance measures one by one. We will start with average precision, or AP for short, because this is the de facto performance measure or the most widely used performance measure in visual detection. Suppose we are given a set of detections and a set of ground truth annotations on a number of images. Here we will illustrate the computation of AP over just a single image, just for simplicity. To compute AP, we need to compute the recall precision curve, as AP is the area under the recall precision curve. And to obtain a single point in the recall precision curve, we actually need two thresholds, one for the detection confidence scores and the other for the intersection over union values. Let these thresholds be, for example, 0.3 and 0.5. Given these, the first step is to eliminate detections with confidence scores lower than t is equal to 0.3. On this particular example, there is one detection with score lower than 0.3. This detection has score 0.1. So according to this threshold, it needs to be eliminated. So we eliminate it. The next step is to match the remaining detections with ground truth boxes based on localization quality, that is the intersection over union. We check all possible pairs of detections and ground truths, and if a detection matches with a particular ground truth box with more than the given intersection over union threshold, which is 0.5 in this case, then we declare a match. Here in this example we have two matches. This particular detection matches with this particular ground truth item, and this detection matches with this ground truth item because they both have intersection over union values larger than 0.5. Note that after the matching is complete, there is one ground truth box which did not match with any detection, this one, and a detection that did not match with any ground truth items. Next step is to count the number of true positives. Because there are two matches, as shown here, the number of true positives is 2. We can also count the false positives, which is 1, which comes from this detection which did not match with any ground truth. And we can also count the false negatives, which is also 1, and it comes from this ground truth detection which did not match with any detections. We can also relate these numbers to the total number of ground truth boxes and total number of detections. The total number of ground truth items equals number of true positives plus number of false negatives, and the total number of detections equals number of true positives plus number of false positives. From here, we can now compute recall and precision. Recall equals number of true positives divided by the total number of ground truth annotations. In this case, it turns out to be 2/3. And precision, which equals the number of true positives divided by the total number of detections, is also 2/3. These two numbers together gives us a single data point in the recall precision curve, as shown here. We just obtained a single data point in this curve. Now, if we do a systematic sweep of the threshold value for t and repeat these 3 steps we just described, we will obtain more points in the recall precision curve, and then our plot would be complete. Finally, theoretically speaking, we would obtain a plot that looks like this, and the area under this curve is what we call average precision, or AP. However, what happens in practice is that you get a non-monotonic curve, because when you, for example, decrease the threshold t a little bit, the recall might stay the same, but precision might decrease. That is why you get these vertical drops and the zigzag behavior. To tackle this, the curve is smoothed out to keep the max precision value to the right at any point. This is called precision interpolation, and this red curve is the result of that interpolation. In the two most widely used data sets in object detection, which are Pascal VOC and MS-COCO, this smoothing is being automatically done for you in the dataset's official evaluation code. Finally, the last step is to compute the area under this curve. In Pascal VOC, area under the curve is approximated by summing the curve over 11 regularly spaced points in the recall axis. And COCO does the same thing, but it uses 101 points. The Pascal dataset uses only one intersection over union threshold, which is 0.5, and hence the name AP50. But the COCO dataset uses 10 different intersection over union thresholds in this range from 0.5 to 0.95, and this produces 10 different AP values, and these are averaged together to get a final AP value. Lastly, note that we plotted this curve for just a single object category. In our example, it was the zebra category. Usually in visual detection datasets, there are many object categories, and to report an overall performance on the dataset, AP values over classes are averaged. This is called MAP in Pascal VOC and just AP in COCO. There are well-known limitations of AP, and we are going to talk about these in depth in the second part of the tutorial. Here we will briefly mention two of them. First, localization quality is only loosely taken into account in AP, so it is actually not properly accounted for. For example, given this particular object and its ground truth annotation, let us consider these three detections. This one seems to perfectly overlap with the ground truth box, and this one seems to cover only the top half of the ground truth item, and this one covers the lower half. But all of these three detections have intersection over union scores that are larger than 0.5, and because of this fact, they are equally good for AP 50. And this is a limitation for AP. It does not properly factor in the localization quality. Another major limitation of AP is that it lacks interpretability. The AP score itself does not provide any insight in terms of the important performance aspects, namely false positive rate, false negative rate, and localization error. Here we see outputs of three different object detectors on the same input image. The blue color boxes denote ground truth, white colors denote true positives, and orange ones are false positives. These three detectors have different strengths and weaknesses. For example, in the first one, let me open the laser pointer. In the first one, there are two true positives with very high intersection over unions, but two other objects are missed, this one and that one. In the second detector, all four objects are successfully detected, but some of them with low confidence scores. And also, there are many false positives, these orange boxes. In the last detector, detector 3, again, 4 objects are detected. There are 4 true positives, but this time with even lower scores overall, and there are now fewer false positives. Obviously, these 3 detectors have 3 different cases. Yet, these 3 different results with very different characteristics yield the same AP score. As you can see here, AP 0.5, 0.5, 0.5. We will talk about this and other limitations of AP in the second part of the tutorial, but this example just shows that AP lacks interpretability. Now let's move on to our next performance measure, which is the Localization Recall Precision Error Metric, or LRP for short. LRP was proposed in ECCB 2018, and it was extended with more analysis, applications, and extensions in the Pattern Analysis and Machine Intelligence Journal in 2021. Let us walk over how LRP is computed by revisiting the same object detection example that we used for explaining average precision. As in the case of AP, we need 2 thresholds, one for the confidence score and the other for the intersection over union. Let's pick the same threshold values as we did before, 0.3 and 0.5. Given the 0.3 score threshold, detections with lower scores should be eliminated first. This is the first step of the computation. Then we match detections to ground truth boxes based on their pairwise intersection over union values. And as a result, we have 2 true positives, 1 false positive, and 1 false negative. And this one was already eliminated. So these are our numbers. Okay. LRP between a set of detections and a set of ground truth boxes is computed as a ratio of total matching error and the total sources of error. So LRP's maximum value can be 1 and its minimum value can be 0. Let us first look at the total matching error. This expression represents the total matching error. In this expression, we take into account all types of errors: false negatives, that is the misses, false positives, and the localization errors of true positives. Each true positive in the detection contributes to the LRP error proportional to its localization error, which is 1 minus the localization quality of that particular detection. One obvious choice for this LQ function is the intersection over union, and this is divided by 1 minus tau, where tau is the intersection over union threshold. This division ensures that for each true positive we have a localization error between 0 and 1. Each false positive contributes to LRP by 1, and similarly each false negative contributes to the LRP error by 1. The sum of all matching errors is divided by Z, which is the sum of all total possible error or total sources of error, which is the summation of false negatives, false positives, and true positives. Now let's consider some extreme cases of this expression, this LRP, to better understand how it works. Suppose all detections matched ground truth boxes, so that we have 0 false negatives and 0 false positives. In this case, the only error to contribute to LRP would be the localization errors, this term. Note that in the case of AP, because any localization above the intersection over union threshold is good enough, recall and precision values would not change. Now, suppose all detections were false positives, then we don't have any true positives or any false negatives. And in that case, LRP would simply be number of false positives divided by number of false positives, which is 1, and that is the maximum possible value for LRP that LRP can take. LRP can be written in a different way. It can be expressed explicitly in terms of its localization, recall, and precision components. LRP localization component gives us the average localization error computed over all true positives. Recall error is basically 1 minus recall, which equals 1 minus number of true positives divided by the number of ground truth items. And then the precision error is 1 minus precision, which equals 1 minus the number of true positives divided by the number of detections. In this way, through its components, we can explicitly obtain performances regarding different aspects of a visual detector. For example, you can compare 2 different object detectors by just looking at their values over these components and tell that which detector is weak or strong in terms of which aspect, and so on. So far, we have seen the computation of LRP for just one specific confidence threshold T. A systematic sweep of confidence threshold T yields this curve. It's called the SLRP curve. On the x-axis, we have the confidence score thresholds, and on the y-axis, we have the LRP values. We call the minima in this curve as optimal LRP, or OLRP for short. It represents minimal achievable LRP error, and this point represents the overall performance of a visual detector. As with LRP, OLRP is also interpretable and it can be separated into its three components. These three values, without the need for looking at any curves or plots, would give us insights about the strengths and weaknesses of the visual detector. We do not need to compute separate LRP or OLRP values for different intersection over union thresholds. We will talk more on the analysis of LRP and how it addresses all the limitations of AP in part 2. And in part 3, we will talk on how LRP can be used as a training objective so that the training and evaluation of visual detectors is unified for improved performance. So far, we explained LRP over an object detection example. But can it be applied to other visual detection tasks? The answer is yes. All you need to do is to define an appropriate localization quality function for the task. So let's take key point detection as an example. An appropriate localization quality for this task is what is called the object key point similarity function, OKS for short. It basically computes the distances between the ground truth point and the predicted point. Then negative of this is passed through an exponential function. Finally, you plug this in the LRP formula. This OKS is substituted here for LQ. And the rest is just the same with the object detection case that we described in the previous slides. We do a systematic sweep of the confidence threshold T and obtain an LRP curve, the minimum of which gives us OLRP or the optimal LRP point. For more applications and extensions of LRP, you can visit our paper. Alright, now let's look at another performance measure called the panoptic quality, and panoptic quality was proposed in CVPR 2019. Unlike AP and similar to LRP, PQ or panoptic quality properly takes into account recall, precision, and localization. Here is its formula. It is similar to that of LRP in structure, but unlike LRP, which is an error metric, PQ is the higher the better measure, similar to AP. So let's look at this expression for panoptic quality. As the localization quality, which is intersection over union here, denoted by IOU, as the localization quality increases or the intersection over union quality increases, the PQ will increase. And as the number of errors, like number of false positives and number of false negatives, then PQ will decrease accordingly. PQ can be written as a product of two quality measures, segmentation quality and recognition quality. Segmentation quality represents the average intersection over union of the true positives, and recognition quality represents the classification performance in the form of an F measure. Overall, panoptic quality is interpretable in the sense that segmentation and recognition qualities are separately computed and can be reported. However, its interpretability is limited since recall and precision are not explicitly given. And finally, panoptic quality is limited to hard predictions. These are those predictions without confidence scores. Theoretically, PQ can be extended to evaluate soft predictions, but this extension was not provided in the original paper. We will talk more about PQ and its analysis in terms of desirable properties of a performance measure in part 2. After covering AP, LRP, and PQ, now we will go over more recently proposed performance measures. The first measure we are going to look at is the recently proposed AP variants, which are AP fixed and AP pool. In this paper, the authors showed that AP, as it is implemented in the common benchmarks, for example COCO, is actually gainable. they discover an unintuitive re-ranking strategy that can increase AP substantially, in this example from 25.5 to 27.2, by reducing the number of detection outputs for frequent classes, person in this case, and increasing the number of rarer classes, bicycle in this case. This re-ranking balances AP better across categories, but counterintuitively removes some higher confidence true positives while also adding some lower confidence false positives as shown in this figure. The root cause for this phenomenon is that the standard AP implementations limit the number of detections per image. For example, in COCO, it is limited to 100 per image. And this creates problems. Rare classes are disfavored and because they usually have lower confidence scores. Cross-category confidence calibration is ignored, and AP for a single class is not really independent from other classes. To fix these issues, the authors propose AP fixed. Instead of limiting the number of detections per image, they limited per class over the entire dataset. This ensures class-independent evaluation, so AP is not gameable anymore. However, the cross-category score calibration is ignored. As a better evaluation measure that takes into account cross-category calibration, they propose AP pool. As we said in the previous slide, standard AP and AP fixed compute AP per class and then take average. This ignores cross-category score calibration. To reliably take this into account, AP pool pools detections from all images of all classes, and a single recall precision curve is computed. And this rewards properly calibrated detectors. The next performance measure to visit is the probabilistic detection quality proposed in WACV 2020. This paper actually proposes a new task. It is the probabilistic object detection, where uncertainties regarding both the semantic label and the spatial support are taken into account. For example, on the spatial aspect, instead of directly outputting bounding box coordinates, the probabilistic object detector outputs distributions for the top left and bottom right corners for an object. And these two distributions together define a spatial probability distribution as shown in this figure. PDQ can evaluate such probabilistic outputs, but it can also evaluate conventional object detection outputs with box coordinates. In PDQ, for all possible detection and ground truth pairs, PPDQ is computed. This consists of a spatial quality term times a label quality term. Based on these PPDQ values, a Hungarian matching algorithm is used to establish which detection matches with which ground truth. Then, overall PDQ is computed using this formula, which is structurally very similar to PQ and LRP as well. Here, this Q function is actually PPDQ, which measures the spatial quality and label quality for a detection ground truth pair, matched pair. And then this total quality is divided by the number of true positives, number of false negatives, and number of false positives. Spatial quality can take into account the mask of the object. This is an additional feature of the performance measure. And PDQ can evaluate probabilistic spatial outputs. The next performance measure is boundary intersection over union. This is a measure that is specifically proposed for segmentation tasks. And here is a motivational figure from the paper. Here we see 3 segmentation results, as shown here, for an object whose ground truth segmentation is given on the top left. The usual quality measure used in this task is mask intersection over union, and although this measure ranks these detections correctly, it is not very sensitive to the qualities of the boundary, as you can see from the differences between these three results. The new boundary intersection over union, however, is very sensitive to the boundary quality, and it intuitively better measures the segmentation quality as demonstrated by these numbers. Given ground truth mask G and the prediction mask P, boundary intersection over union first computes the set of the original mask's pixels that are within distance d from each contour, and then computes the intersection over union of these two sets. So you basically compute these blue region and orange region, which are within distance d from each contour, and then we apply intersection over union on these blue and orange regions. The last performance measure we present in this tutorial is the optimal correction cost, which is from this CVPR actually. Authors in this paper start by illustrating deficiencies of AP very well. This example from the paper shows the output of 3 detectors on 3 different images. So each row is a different detector and each column is a different input image. In terms of AP, this column, the best detector is the third one, this one, because it performs perfectly for the donkey class and it achieves a perfect score of 1, but it misses all instances of ducks and it achieves a AP score of 0. And when you average AP scores over classes, you get 0.5. On the other hand, detector A and detector B achieve equal AP scores, 0.28, although their correct detections are not distributed homogeneously. The first one gets 2 correct detections in the first image and 1 correct detection in the second image, but the detector B gets all the detections correctly in the first one, but none in the second one. So this example basically illustrates the biases of AP over images and over classes as well. As a fix, the authors propose the optimal correction cost. So given a set of detections here and the ground truth items, they first construct a cost matrix. Each element in this matrix represents the cost of correcting that pair of a detection and the ground truth. And correction includes correcting its label plus its localization quality. After this cost matrix is constructed, optimal assignment of the detections to the ground truths are determined by solving an optimal transportation problem. And this gives us this labeling, which denotes the optimal assignments. And based on the assignments, they aggregate the correction costs as the measure of final detection performance. And here we complete the first part of the tutorial. In the next part, we will talk about desirable properties of a performance measure, and we'll present a detailed analysis of AP, LRP, and PQ in terms of these properties.
So thank you for listening to the first part. If there are any questions, we can take. Okay, if there aren't any questions, we can take a 10-minute break. But we are here. Let us know if there are any questions. Okay, thank you for your patience. I am starting the part 2.
Hello everyone, my name is Sinan Kalkan from the Department of Computer Engineering, Middle East Technical University. It's my pleasure to deliver the second part of our tutorial. Note that our tutorial has 3 parts. In the first part, my colleague Emre introduced the basics of evaluating visual detectors. Namely, he motivated and briefly described different visual detection tasks. Then he talked about different localization qualities used in visual detection tasks. After that, he introduced commonly used performance measures in visual detection. Finally, he provided a quick overview of the recently introduced performance measures. In this part, in the second part, now I will talk about the analysis of performance measures for visual detection that we performed in our recent paper. And in the third part, my colleague Kemal will cover how performance measures can be optimized. Let us look at closely what we are going to talk about in this part of our tutorial. We have 2 main sections for this part of our tutorial. In the first section, we will look at first how we can analyze and compare performance measures. For this end, we will first introduce some important features that we expect a performance measure to have. These features will facilitate analyzing how good a performance measure is for evaluating different visual detection tasks. Then we will evaluate average precision and panoptic quality with respect to those important features. We will see that average precision and panoptic quality do not satisfy some of the important features that we expect from a performance measure. In the second section of this part of our tutorial, we will first introduce localization, recall, precision error in detail. Note that Emre provided a brief introduction to LRP error in the first part of our tutorial. In this part, I will provide a more detailed introduction. And I will show that LRP error actually satisfies the important features expected from a performance measure. Finally, I will provide a comparison of LRP error with average precision and panoptic quality in terms of their theoretical aspects and empirical behaviors. Okay, let's start with the first section of this part of our tutorial. In this section, as I mentioned before, we will introduce 3 important features and analyze average precision and panoptic quality with respect to those features. Let us look at the important features that are expected from a performance measure. These important features are completeness, interpretability, and practicality. Now let me introduce them in detail. The first important feature is completeness. We would call a performance measure complete if it considers precisely all 3 performance aspects of a detector. To motivate why we expect a performance measure to be complete, consider the object detection problem. We can easily extend this example to other visual detection problems. In object detection problem, we are provided an input image as shown here, and we are interested in finding the boxes that bound or surround the objects in the image. This detection problem includes 2 tasks. A classification task for finding the class labels of the objects, zebra in this example image, and a localization task for estimating the coordinates of the box that bound the object. The coordinates of the center and width and height of the box, for example. We can clearly see that the object detection problem includes 2 tasks, a classification task and a localization task. Therefore, the performance measure designed for evaluating object detection problem should quantify both aspects of the detection problem. This includes false positive rate and false negative rate for the classification aspect of the problem, and the localization error for the localization aspect of the problem. If a measure is not evaluating any of these quantities, then it's not completely quantifying all aspects of the detection problem, as it is missing at least one aspect. And we will call such a measure incomplete. The second important feature is interpretability. We would call a measure interpretable if it provides insights on the strengths and weaknesses of the detector. In other words, detectors can have different characteristics. One can be good at, for example, classification, while another detector can be good at localization. And we expect the measure to provide insight about these different performance characteristics. To illustrate, let us look at the object detection problem again. Here we have an example input image, and let's say we have a detector that detects these 2 objects out of the 4 objects drawn in blue. Here we see that detector 1 is not providing an ideal performance, as it's providing a high false negative rate. We can easily find another detector which provides high number of false positives instead, and we can consider another detector that provides high localization error instead. If a performance measure does not provide an insight about these different performance behaviors, then it's difficult to understand what is wrong with our detector, and we would have difficulty comparing the performances of different detectors. Therefore, a performance measure should provide an interpretability insight about the performance of the detector. The third feature is practicality. We can call a performance measure practical if it provides some practical benefits and if it does not have any practical issues during its calculation. What could those benefits and issues be? For example, are we able to apply the measure if we have the so-called hard detections? In other words, detections that do not have any confidence scores. Or is the measure able to provide any help for finding the optimal confidence threshold for the detections? Is the measure robust to design choices? For example, to the interpolation or approximation of a curve, or the number of detections per image or class. We will see that performance measures have different benefits and issues when they are applied in practice. Now, let us look at the commonly used performance measures and analyze where they stand with respect to those important features. Let us start with average precision. My colleague Emre introduced average precision in the first part, so I will directly start with analyzing average precision with respect to the important features. Let us look at average precision in terms of the completeness feature, our first important feature. Consider these 3 different detectors which have very different classification and localization behaviors. When you look at their precision and recall curves, we see that they are actually quite different, indicating different problems with the detector. However, if you calculate average precision as the area under these curves, we see that actually average precision value is the same for all these 3 detectors. In other words, average precision does not consider all performance aspects, especially localization. Let us continue with the second important feature, interpretability. We expect a measure to provide insight about the problems of the detector in the interpretability feature. Consider the same example from the previous slide, where we have 3 different detectors with different performance characteristics. We see that average precision provides the same performance of 0.5 for these very different performance behaviors. As such, users of these detectors would not have any idea about which parts of their detectors are failing and which parts are performing well. Therefore, we say that average precision does not satisfy the interpretability important feature. Now let us look at some practical issues which might arise when one uses average precision. First of all, average precision is not suitable in settings where the detections do not have confidence scores. Why? Because average precision is a ranking-based measure and it assumes confidence values to be available for ranking the detections as shown here, and for calculating the precision recall values for each detection and plotting them and obtaining the precision recall curve. If confidence scores are not available, one can calculate only a single precision recall value. Another practical issue with average precision is that it does not facilitate finding an optimal threshold for the confidence of detections. If you lower the confidence threshold, average precision increases because we go towards higher recall values and a larger area under the precision recall curve is covered. With a threshold of 0, all detections are included and average precision obtains its maximum value. Therefore, by looking at average precision values, we cannot determine the optimal threshold. Another practical limitation of AP is that it is sensitive to how it is calculated. After the precision recall curve is calculated from the precision recall values of the detections, we see in general these ups and downs, which are generally smoothed by using interpolation. Then, at a discrete set of recall values, precision is calculated and averaged in order to approximate the area under the curve. We have shown that these steps significantly affect the calculated AP values for classes with few examples, and therefore the calculated AP values may not reflect the true performance of the detector. One final note about the practical issues regarding average precision is that it is sensitive to the number of detections allowed per image, which is the standard mechanism for evaluating detectors in detection benchmarks. This is, for example, 100 detections per image for the COCO dataset. It has been shown last year by Dave et al. That this can actually introduce some bias against less frequent classes. This limit can be changed and defined for each class, which however still introduces a bias in AP against certain classes. If we summarize our analysis of average precision with respect to the important features, we see that average precision does not satisfy any of the important features we defined. To be specific, average precision is not complete, it is not interpretable, and it has several practical issues when we use it in practice. Now, let us continue with the analysis of panoptic quality, which was introduced in the first part of our tutorial. Note that panoptic quality was proposed independently with LRP error and in a similar time frame as LRP error. Let us analyze panoptic quality in terms of the completeness feature, like we did for average precision. We see that panoptic quality can be written in this form, which includes the number of false positives, the number of false negatives, and a localization error for each true positive. Therefore, we can say that panoptic quality satisfies the completeness feature expected from a performance measure. If you look at interpretability, we see that panoptic quality is doing better than average precision in this regard as well. One can easily rewrite panoptic quality and show that it has two main components. A component for measuring the segmentation quality and another component for measuring the recognition quality. Segmentation quality is an average of intersection over union of the true positives, and recognition quality is evaluating the classification performance, and it is an F measure. Therefore, since panoptic quality has interpretable components, it satisfies the interpretability important feature. However, the recognition component is an F measure, and it is not able to distinguish between different precision and recall performances. Therefore, we can say that panoptic quality satisfies the interpretability feature, though it has a limitation in this regard. If you look at the practicality aspect of panoptic quality, we observe that the authors in their original paper applied panoptic quality only to panoptic segmentation, and it is designed to evaluate only hard detections. the authors assumed that segments did not have confidence scores. However, in theory, it's possible to apply panoptic quality to soft detections by a simple thresholding operation. A more severe practical issue with panoptic quality is that it over-promotes classification with respect to localization. Here we see an example. Consider that we are slowly increasing the quality of our segmentation by adding these slices, step by step. With each step or slice, we calculate the corresponding panoptic quality and we plot it here as shown at the right-hand side. Here we see that when a detection becomes a true positive, there is a jump in the panoptic quality value. And after this point, the contribution of the localization quality is minor, corresponding with respect to the classification performance, and its localization quality can contribute only between 0.5 and 1. Because of this discontinuity, PQ does not specify the triangle inequality, and it is not a metric. A more detailed proof of this is available in our paper. We will show later that the way panoptic quality combines classification and localization is actually inconsistent. To summarize, we have shown that panoptic quality is complete because it takes into account false positive rate, false negative rate, and localization error for true positives. It is interpretable because it has two components, segmentation quality component and recognition quality component, but limited in terms of interpretability because the recognition component is an F measure and it does not provide information about precision or recall independently. Finally, it has certain practical issues when it is used in practice. Now, let us look at localization, recall, precision error, in short LRP error. First, I will introduce LRP error in detail. Then we will analyze LRP error in terms of the important features similar to how we analyze average precision and panoptic quality. Note that LRP error was introduced independently from panoptic quality in 2018. In the first part of our tutorial, Emre introduced LRP briefly, and now I will provide a more detailed coverage. LRP error includes number of false negatives, number of false positives, and a localization error for each true positive normalized with respect to 1 minus localization threshold tau. We can call this part total matching error, which is normalized by the total source of error in order to make sure that LRP takes values between 0 and 1. We can rewrite LRP error as a summation of three components: a localization component, a false positive component, and a false negative component. Let us go through an example to see how LRP error can be calculated. Let's go through this example image for which we have these objects as ground truth. Let's consider a detector which provides these boxes as detections. If we threshold these detections by 0.95, we obtain a single object, and for this case, the number of false negatives is 2, the number of false positives is 0, and we can easily calculate the localization error normalized. We can add them up, obtain total error, we can normalize it with 3 and obtain an LRP value of 0.70. We can lower the threshold and obtain a second object detected. Then the number of false negatives is reduced. We can calculate the number of false positives, the other quantities as well, and we can easily calculate the number of LRP error. We can lower the threshold even further, obtain a third box, third object. We easily see that the LRP value is reducing with the addition of each object. If we lower the threshold too much, we end up with a false positive as the output of the detector. And we see that the number of false negatives is now 1, and the LRP value increases. If you look at all these LRP values, we see that it is lowest for this threshold. So among the LRP values, the lowest LRP is called the optimal LRP value, and in this case it is 0.47. And we can analyze the components of LRP for this optimal setting, and it gives important cues about the performance of a detector. And this threshold that led to the optimal LRP value is critical. We can easily formulate this optimal LRP error as the smallest of LRP values that can be obtained with different thresholds on the confidence score. If we disregard localization on the precision recall curve, this would correspond to an optimal precision recall value, which is this point, the point closest to 1, 1 on this curve. However, in LRP, we have 3 axes: precision, recall, and localization. And optimal LRP is the point on this curve that is closest to 1, 1, 1. In a 1D plot, we can plot confidence score thresholds with respect to LRP values, and optimal LRP is actually this point, the minimum point of this curve. And this score is then the optimal threshold for this detector. Optimal LRP has 3 components, and looking at these components gives an intuition about the performance of a detector in terms of localization, false positives, and false negatives at its best setting. In LRP, plotting confidence scores against LRP values gives important clues about the detector. We find these plots very important, and we call them S-curves. We can analyze the S-curves for different detectors and for different classes. For example, for the person class, we see that faster RCNN is providing its best values around 0.60 LRP with a confidence score of 0.70, whereas it provides its best performance with a confidence score of 0.50. We see that S-curves can provide insights, similar useful insights for other detectors and for other classes as well. We can draw an important conclusion from these curves. These S-curves suggest that detectors should have different thresholds for different classes. Why? Because the optimal LRP values are obtained for different thresholds, for different classes. Moreover, we see that detectors provide very similar optimal LRP values for the broccoli class, whereas that is not the case for the person class. After having introduced LRP in detail, now let us look at how it fares in terms of the important features we introduced. Let's start with the completeness feature. In terms of completeness, we see that LRP includes number of false negatives, number of false positives, and localization error for true positives. Therefore, we can easily say that LRP is complete. In terms of interpretability, we can rewrite LRP error as a summation of 3 components: a true localization component, a false positive component, and a false negative component. Therefore, using LRP error, we can interpret the types of errors a detector is making. Therefore, we can say that LRP error is interpretable. If you look at the practicality feature, we showed in our paper that LRP error can be used for hard detections and soft detections. LRP error does not require any interpolation or approximation. And unlike average precision and parameter quality, LRP error is a metric. Therefore, we can say that LRP error is actually practical. It does not have any practical issues in practice. If we summarize how LRP error performs in terms of the important features, we showed that LRP is complete because it considers false positive rate, false negative rate, and localization error, similar to panoptic quality. It is interpretable because it can be written as a summation of three components: a localization component, a false negative component, and a false positive component. And it does not have any practical issues when we want to use LRP error in practice. Therefore, we can say that LRP error satisfies all three features, unlike average precision or panoptic quality. Now, let's go through some theoretical and empirical analysis to get more insight about these measures. To be able to better compare average precision, panoptic quality, and LRP error, let us transform all of them to be error values. In other words, after this transformation, all of them will be lower better measures. Average precision uses soft predictions. For comparison with LRP and panoptic quality, we use its hard counterpart, which corresponds to a single precision and recall value. We can transform this precision recall into an error by subtracting their multiplication from 1. Let's call this precision recall error. Panoptic quality can be transformed into an error by subtracting it from 1. Let's call this PQ error. We can easily show that PQ error can be written in this form, where we have number of false positives, the number of false negatives, and a normalized localization error for each true positive. The normalization here is 1 minus 0.5, where 0.5 is the localization threshold. And we have a normalization constant here, which is a summation of number of true positives multiplied by 2, number of false positives, and number of false negatives. LRP is already an error, so we don't need to do any transformation on that. And we already saw that it includes number of false positives, the number of false negatives, and a normalized localization error. And the normalization constant here is the number of true positives, the number of false positives, and number of false negatives. We see that PQ error and LRP error are actually very similar to each other, except for two parts. One part is that the normalization constant has a multiplier in front of the number of true positives for PQ error, and this favors the number of true positives more than it does the number of false positives and the number of false negatives. The second difference is with respect to the localization quality. In PQ error, localization quality is normalized with respect to a constant localization threshold, whereas in LRP error, this is a hyperparameter. When we look at how these errors are distributed in a three-dimensional space, spanned by the number of true positives, the number of false positives and false negatives, and localization quality, we see that LRP error is uniformly and continuously changing with a change in any of the axes. Whereas average precision or its error version does not include localization. Therefore, a change in localization quality does not affect PR error or average precision. When we look at panoptic quality, we see that panoptic quality is not consistent about how much it is changing with a change along different axes. The reason is this denominator, where we have a constant multiplier in front of the number of true positives, which favors true positives more than false positives and false negatives. Therefore, it's not consistent in terms of how it handles localization quality, true positives, and false positives plus false negatives. If you plot LRP error with respect to 1 minus precision, 1 minus recall, and 1 minus PQ, that means the PQ error, we see that LRP is always higher than these values for different LQ values. Therefore, LRP can be considered as an upper bound for 1 minus precision, 1 minus recall, and 1 minus PQ. And in turn, this means that optimizing LRP is actually a more challenging problem than optimizing the other measures. If you compare all measures in terms of important features, we saw that average precision does not satisfy any of the features. Panoptic quality performs better than average precision in that it is complete. It is interpretable, though its interpretability is limited, and it has some practical limitations. We saw that LRP satisfies the 3 important features, and therefore we can say that it is a more suitable measure than others for visual detection problems. Now let us look at some experiments that illustrate the use of these measures. We can look at soft detection problems, such as object detection, key point detection, instance segmentation. We can analyze and compare these measures on hard detection problems, such as panoptic segmentation. We can analyze these measures on different datasets and different detection tasks. And we can show that LRP actually can be used for optimally thresholding a detector. But because our time is limited, we won't be able to look at all the empirical results that we have. And if you are interested in more comprehensive results and analysis, you can check out our paper. In our paper, nearly 100 state-of-the-art visual detectors from 7 visual detection tasks using 10 different datasets are used to empirically show that LRP error provides richer and more discriminative information than its counterparts. If you look at the object detection problem, which uses soft detection outputs, in that we have confidence scores for each detection, we see that average precision actually is not capturing the overall performance of a detector very well. For example, NAS-FPN is expected to perform better than GHM in terms of localization, and with average precision, to compare the performance of detectors in terms of localization, average precision at 0.75 intersection over union threshold is used, and we see that actually AP75 value for NAS-FPN is actually lower than that of GHM, which is counterintuitive. If you look at the optimal LRP values, the localization component of optimal LRP, we see that as expected, NAS-FPN is actually doing better than GHM in terms of localization quality. If you look at average precision in terms of interpretability, we see limitations as well. For example, if you compare faster RCNN with ATSS, APC values are the same, whereas AP at 0.50 and 0.75 intersection over union thresholds are different, and average recall values are different as well. As such, average precision, overall average precision is not sufficient for comparing methods, and AP does not provide an insight about the characteristics of the performance. If you look at LRP on the other hand, we can clearly see that ATSS is doing better than faster RCNN in terms of localization, and faster RCNN is doing better than ATSS in terms of false positives and false negatives. Therefore, with this simple analysis, we can see that LRP provides more insight about the weaknesses of a detector and its strengths. If you look at these measures in terms of practicality, we see that LRP can be used for soft or hard detections, for optimally thresholding detectors, and it does not have any interpolation or approximation issues. If you compare panoptic quality and LRP in terms of completeness, we see that both are complete, since they both incorporate the number of false positives, the number of false negatives, and localization while measuring performance. In terms of interpretability, both methods are interpretable. They provide performance in terms of localization and classification. However, PQ uses an F measure in the recognition component, which is not interpretable in terms of precision or recall. Finally, in terms of practicality, pump to quality has certain limitations. As we noticed before, pump to quality over promotes true positives, and there's a discontinuity in PQ values. In our paper, we evaluated these measures on different tasks and datasets with different characteristics. For example, on the Elvis dataset, we did an analysis with respect to rare classes. We looked at the effect of increasing the number of detections per image. We realized that every average precision is severely affected by this change, whereas LRP is more robust against this change. And we have more results on open images, Pascal and Coca datasets on different types of categories, object categories. If you look at a different detection task, for example, visual relationship detection or zero-shot detection, we see that LRP is providing more insights than average precision in all these problems. We also analyzed how optimal thresholding scores for different detectors change. We note that different detectors have different optimal thresholding score distributions, and these scores depend on classes. Our results confirm that thresholding detections differently for each class can be beneficial. We note similar behaviors among different class categories, rare, common, and frequent class categories, for example, and similar observations can be made for different zero-shot detection approaches. We can conclude the second part of our tutorial with these results. In this part, we introduced 3 important features with which we can analyze different performance measures for visual detection. With these important features, we saw that the widely used average precision measure has significant limitations in terms of completeness, interpretability, and practicality. Our analysis on panoptic quality indicated that panoptic quality is doing better in terms of these features. However, there are certain practical limitations with panoptic quality as well. We introduced LRP error in this part in detail as an alternative, and we showed that it does better than average precision and panoptic quality in terms of these important features. Now we will give a break, and after the break, we will continue with the third part of our tutorial. Thank you. If you have any questions, we can take them actually now before the break. Okay. If there are no questions, then we can take a break. We will be here, so if you have a question, we can take your questions via chat. Thank you.
Okay, we will start the third part in a few seconds.
Hello, I'm Kemal Öksüz, and in the last part of this tutorial, I will discuss optimization of performance measures. In this part of the tutorial, we will focus on how the performance measures can be optimized as loss functions. The main challenge in this optimization is that such loss functions derived from performance measures are non-differentiable. And to overcome this challenge, we will revisit identity update as a general framework to obtain loss functions from average precision and LRP error. The first question to ask in this part of the tutorial is whether optimizing a loss function always implies optimizing the performance measure of a task. Even comparing the widely used cross entropy loss function with accuracy presents that it does not. Let's assume that we have three different classes and three examples, each of which belongs to a different class. And during training, we obtain two different sets of predictions of these three examples, prediction 1 and prediction 2. Comparing prediction 1 and prediction 2 in terms of cross entropy and accuracy, we can observe that while prediction 2 has a lower loss value, prediction 1 has a higher accuracy. This presents a counterexample on a case where optimized loss function may not optimize the performance measure. Then we can ask a follow-up question. Why don't we use performance measures as loss functions? This is mainly because computing performance measures in general involves non-differentiable counting operation. I use the term non-differentiable to refer to an operation when its derivatives with respect to its inputs are either 0 or infinity. Let me present the problem on a toy example. Stochastic gradient descent update rule, which dominates the optimization of deep learning models, updates a learnable parameter of the model, Wi, by using the derivative of the loss function with respect to Wi. This derivative can be decomposed into two multiplicative parts. The first part, the derivative of the model output with respect to the weight, comprises of sequential differentiable neural network layers and can be computed using backpropagation. On the other hand, the second part, the derivative of the loss function with respect to a network output, Sj, depends on the loss function. Comparing cross entropy and the loss form of accuracy, we can see that while cross entropy loss has a smooth surface providing useful derivatives for stochastic gradient descent throughout its domain, accuracy loss has a step-like structure with only derivatives of either 0 or infinity, hence it cannot be directly incorporated into stochastic gradient descent. We will refer to such functions as ranking-based loss functions, which can be defined as the loss functions involving a Boolean comparison psi between two different model outputs Si and Sj. The comparison function can be represented by Heaviside step function h, considering the differences of these model outputs, which is non-differentiable. As an example, on binary classification task with positive and negative classes, we can define a loss function as the average number of negative examples ranked over positive examples, namely the number of false positives, which can be represented by the expression in the screen. Then, given 5 examples from positive and negative classes with the shown confidence scores, this loss function is minimized when all positives are ranked above all negatives. And it is computed by thresholding the detections on each positive and counting the number of negatives ranked above the corresponding positive. Thresholding from the first positive, we have one negative ranked above that positive, and for the second positive, there are 3 negatives. Accordingly, the overall average loss value for this toy example is 2. In this part of the tutorial, I will first introduce identity update as a general framework to optimize these ranking-based loss functions. And then I will discuss how average precision and LRP error can be converted into loss functions by using identity update framework. More particularly, I will introduce average precision loss for classification tasks, and then for visual detection tasks, I will introduce average LRP and rank and sort losses, both of which rely on LRP error introduced in the first and the second part of this tutorial. Let me begin with identity update. Let's briefly revisit perceptron learning, since identity update relies on error-driven update from perceptron learning. Perceptron aims to learn a weight vector W that classifies the input X between two classes. As an example, assume that there are two examples from negative class and one example from positive class, and we want to split positive and negative classes by a hyperplane represented by its normal, the green arrow in the figure. The general convention is to initialize the normal vector randomly and then, having observed the data, update it according to improve the classification performance. One of the most straightforward approaches can be to set the normal vector to the example itself when the observed data belongs to the positive class and the model makes a mistake predicting it as a negative. Else, if the label of the observed data is negative and the prediction is positive, it is set to the opposite direction of the example. However, with such an update rule, the normal vector will oscillate and not converge. Instead of these large changes, error-driven update aims to update the weights slowly when the model makes a mistake. For example, having observed the positive example in this setting, the normal vector is shifted towards this example slowly. The corresponding error-driven update can be simplified into a single equation such that W is the model parameters, X is the input data, T is the prediction of the model, and T star is the target label of the data. Inspired by the work of Chen and his colleagues, identity update uses error-driven update from perceptron learning, and it is proposed as a general framework to optimize ranking-based loss functions. It assumes a ranking-based loss function to follow the form in the left side of the screen, in which the loss is the normalized sum of the differences between the current error computed on example I, that is Li in the screen, and its target value, that is L star I in the definition of the loss. For example, for our toy example, Li is the number of negatives ranked over ith positive. The target term is 0, since the number of negatives is 0 when we rank all the positives above negatives, and the normalization constant is the number of positives. In order to generalize the idea, we need to answer two questions. First, how can we compute the ranking-based loss function given model outputs? And second, how can we find an update for model outputs, namely the backpropagation step? To do so, identity update exploits a three-step algorithm. First, the differences between each pair to obtain pairwise relations are computed. Then, given these difference transforms, primary terms that are the error originating from each pair are computed such that the normalized sum of these primary terms yields the loss value. To obtain these primary terms, the error computed on ith example is distributed over other examples by a probability mass function. Note that examples other than I contribute to Li. For example, in our toy example loss function, the scores of the negative examples directly affect the error computed on ith positive example. Hence, to obtain pairwise error, the error needs to be shared with its contributors. It has been also proven that this formulation yields to the desired loss value. As for the backward pass, the first and the last steps are differentiable, and it has been shown that the error value can be directly adopted as the update for the second step. and the resulting total gradient magnitudes are equal for positive and negative classes. Note that one only needs to define the loss function and determine a probability mass function, which make the framework general and simple. Now I will continue with average precision loss, AP loss in short. In this part, I will revisit the classification task, derive average precision loss without and with identity update, and finally I will provide an overview of the implementation of AP loss. Average precision loss is proposed as a ranking-based classification loss, and it is used for supervising the classifier of visual detectors. Image classification aims to infer the class label of the input image. To do so, the models output a logit for each class, which is then converted into a probability value. The first alternative to convert the logits to probabilities is to use a softmax function and obtain a probability distribution over classes. And the second common alternative is using class-wise sigmoid classifiers. Throughout this part of the tutorial, I will refer to the ground truth class logit and output as positive example, and output to be maximized, and the remaining non-ground truth classes will be negative examples. Accordingly, from this image, the zebra output corresponds to the positive example, while all others belong to the negative class. Besides, if an image does not contain any of the ground truth classes, then all the logits will be regarded as negative examples. With a similar intuition with our example number of false positive loss function that we discussed earlier, average precision loss is defined as the average of the precision errors on positive examples. Given class labels and network outputs, the aim of the average precision loss is to suppress the output of the negatives and promote the output of the positives, such that all the positives are ranked above negatives where the optimal condition is achieved. Note that the optimal condition is different than this conventional score-based classification losses, such as cross entropy and focal loss, since these score-based loss functions reach to the optimal state when the probabilities of all positives saturate to 1 and the probabilities of all negatives saturate to 0. In order to demonstrate the generalization and simplicity of identity update, I will first present how AP loss is derived by Chen and his colleagues in their pioneer paper. Given model outputs, first the difference transforms are obtained, and then primary terms for AP loss are derived by algebraic manipulations such that the normalized sum of the primary terms yields the loss value. Note that the primary term includes Heaviside step function, and Hxij corresponds to the pairwise relation between the example I and j. If the score of example j is larger than the score of example I, then Hxij is 1, otherwise it will be 0. A hyperparameter delta is introduced to smooth the Heaviside step function, while putting a margin between the samples to be ranked in order to ensure generalization. Other ranking-based terms can also be defined based on those pairwise relations. For example, to find rank I, in the denominator of the primary term, one needs to sum the pairwise relations for the example I with all other examples. Finally, to cover all the pairs in the computation, an additional variable alpha ij is introduced such that alpha ij is 1 only if I is a positive example and j is a negative one. As aforementioned, in the backward path of this computation sequence, the first and the third terms are differentiable while the second one is not. Hence, the authors replace that non-differentiable part by error-driven update, that is the difference between target and current values. And in the target ranking, AP loss aims to rank all positives above all negatives, implying 0 error, namely 0 primary term. Note that beyond generalizing this optimization strategy, identity update offers simplicity, since the primary terms are not derived, but they are defined based on the definition of the loss function, and no additional variable such as alpha is required. Let me introduce how we derive the update with identity update, which includes a three-step framework that are defining the loss function, computing the loss function, and optimizing the loss function. In the first step, we define the loss function from identity update perspective. Namely, we need to define the error value on a single example, that is Li, and its corresponding target, that is L star I. For AP loss, the error is simply the precision error presented at the left part of the screen. And the target on a single positive example is to rank positives above negatives, which implies perfect precision that makes the precision error 0. Then, to compute AP loss following identity update, we obtain the primary terms as the products of the defined errors on a positive example and probability mass function. The probability mass function distributes the error uniformly over other examples, causing the error. More precisely, for positive-negative pairs, the ranking probability mass function distributes the error computed on ith positive uniformly over negatives with logits larger than the ith positive example. This is because if there is ranking error on a positive example, this is due to the negatives with larger scores. This ranking probability mass function expression corresponds to this operation. In such a way, the primary terms as the pairwise errors can be obtained and the loss value can be computed. Note that obtaining primary term using its definition is significantly simpler compared to deriving it. Finally, for optimization, we replace the non-differentiable part by primary terms and simplify the expressions for negative and positive examples. In such a way, we obtain the update expression of the loss function with respect to the logits, concluding the derivation of AP loss, computation, and optimization using identity update. In the left side of the screen, the implementation of AP loss is presented. Different from the conventional score-based loss functions with linear time and space complexity, average precision loss requires the relations between all pairs, and as a result, it has quadratic time and space complexity. This especially makes the training of object detectors challenging, since object detectors can have hundreds of thousands of examples, making it infeasible to use such loss functions directly, especially due to the space limitations of GPUs. To alleviate that, two training tricks are employed. First, the negative examples that do not contribute to the loss, namely the ones that are already classified properly with the desired margin, are discarded from the computation in the beginning of the implementation. And second, instead of computing the update at once, the updates are computed on each positive example sequentially implemented by a loop. Now let's consider the computations in a loop given the example input at the top right of the screen. Note that the loop runs over the positive examples and assumes that the computation is on the green positive example. In the loop, first the precision error LAP is computed, which is 0.6 on the green example, since there are 6 negatives and 10 total examples with larger scores than this example. Note that this error directly corresponds to the normalized update for the positive example. As for the negative examples, in order to implement the probability mass function, the ranking error is divided by the number of negatives, and the resulting error is cumulatively summed within the loop. Hence, the higher a negative has a confidence score, the more update it will receive from other positives to reduce its score. In this example, the update of all black negatives increases by 0.1. Finally, following the update expression, all updates are normalized by the number of positives. The experiments suggest that AP loss performs better than focal loss in object detection tasks on COCO and Pascal datasets. Note that similar to focal loss, AP loss is robust to class imbalance and hence does not require any sampling heuristics to alleviate positive-negative imbalance inherent to object detection. Next, I will continue with average localization recall precision loss, average LRP loss in short. Average LRP loss is designed specifically for object detection, in which the aim is to classify each object in an image also by localizing them by bounding boxes. This slide presents an overview of the common object detection pipeline along with some key concepts. In order to reach the desired output, the image is fed to a backbone network, which can be a combination of ResNet and feature pyramid network, and the features from the entire image are obtained. Then, in the pipeline, there exists a subnetwork for each task. Given the extracted features, the classification network aims to classify the objects, and the localization network regresses the bounding boxes of the objects. In order to capture all objects in different locations, scales, and aspect ratios, the image is divided into sub-regions, which are called object hypotheses or anchors in general. If an anchor overlaps with a ground truth box significantly, then we expect the classification network to classify it with the label of the object and the localization network to map the anchor onto the bounding box of the object. Otherwise, if the anchor does not correspond to any of the objects, then the classifier is to classify it as background and the localization output is irrelevant in this case. Since there are many anchors, the same ground truth can be targeted by several anchors, causing duplicates. Generally, non-maximum suppression, or NMS in short, is employed to remove the duplicates and to yield the final detection output. In some detection pipelines, there can be more than one pair of classification and localization networks, which can be regarded as multi-stage detectors. Finally, to measure the proximity of two bounding boxes, green and blue boxes in the image, intersection over union is adopted as a common overlap measure. As the name suggests, given two boxes, we measure their union and intersection and then estimate the ratio. If the green box gets closer to the blue box, then their intersection will increase and union will decrease, implying a better overlap. IOU is used, for example, while matching the anchors with ground truth boxes. An anchor is positive if it has a large IOU with a ground truth box, else it's a negative anchor and needs to be classified as background. This pipeline is trained by a multitask loss function, in which there exists an individual loss function to train each subnetwork, which are then combined by a scalar lambda. However, this formulation has drawbacks. First, mainly due to the imbalance problems, the methods tend to introduce many hyperparameters. For example, when we simply use cross entropy loss, due to the significant imbalance between positive and negative anchors, the classification loss drops directly to 0 in the beginning of training. This is due to overfitting for background classes, since the network classifies all anchors as background. Note that such a detector effectively does not learn anything. As a common solution, focal loss introduces two hyperparameters, and in general, the number of hyperparameters can easily reach 10, which makes the loss functions of the object detectors hard to be tuned. Besides, this common loss formulation ignores correlating classification and localization networks, which influences the performance. Here I will illustrate the effect of correlation on non-maximum suppression. Let's assume that there are three overlapping boxes, blue, white, and red, which are shown in the top right image on the screen. and non-maximum suppression will survive one of them. If the confidence scores and IOUs of the predictions positively correlate, then non-maximum suppression will survive the one with the best localization as shown in the NMS output at bottom left image. On the other hand, if the correlation decreases, then NMS will end up with the one with the worst localization quality. Note that this loss formulation combines losses independently and ignores this correlation. Finally, as illustrated before, while the pipelines of one-stage and multi-stage methods are similar, the methods employ different techniques to alleviate class imbalance. Commonly, one-stage methods are trained without sampling but with focal loss, whereas multi-stage methods use sampling and cross-entropy. However, a robust solution to class imbalance should be able to train all approaches providing at least the same performance. These three drawbacks can be addressed directly by optimizing performance measures, namely by bridging the gap between training and evaluation. Average LRP loss is an attempt to close this gap. Different from average precision loss, which optimizes precision error, average LRP loss optimizes localization recall precision error, which is a performance metric for object detection combining classification and localization qualities as discussed in the first and the second parts of this tutorial. There are two assumptions while converting LRP error into a loss form. First, assuming that the anchors are dense enough to cover all objects, the number of false negatives is set to 0. And secondly, true positives and false positives are replaced by positive and negative anchors respectively to supervise the training. With these assumptions, averaging the loss form of LRP errors over positive examples, the conventional loss formulation can be replaced by average LRP loss. As a result, both classification and localization outputs are now unified in a ranking-based manner. Average LRP loss is differentiable with respect to the localization branch outputs, since the localization error is based on intersection over union, which is a differentiable function, and the classification branch outputs are constants with respect to the localization branch. Unlike the conventional losses, if a positive example has a relatively larger score, and hence it is ranked higher, first, it will have a smaller rank I, normalizing its error, and second, it will be included in the loss multiple times thanks to its positive pairwise relation H with other positives. With these two changes, the localization branch assigns larger weights on the positive examples with larger confidence scores. The same three-step framework from identity update comprising defining, computing, and optimizing the loss function can be used again. Note that this part corresponds to the current average LRP error, and the target average LRP error is defined by considering the localization quality of an example. To compute average LRP loss, following identity update, the primary terms need to be obtained using the same probability mass function from average precision loss. The resulting expression is the same, except the current and target average LRP errors replace those of average precision loss. Finally, simplifying the expression yields the updates for positives and negatives. Since LRP error assigns a localization error only if an example is a true positive, the localization branch is hardly trained, especially in the beginning of the training. To show that, average LRP loss can be split into classification and localization parts. The figure in the screen presents their trend during training. Note that in the beginning of the training, the classification part dominates the bounded range of average LRP loss, which is between 0 and 1. Also, the rate between classification and localization parts varies throughout the training. Moreover, the sum of the gradients in the classification branch approximates the loss value. Using these observations, average LRP loss employs a dynamic and hyperparameter-free self-balancing mechanism. Instead of a scalar weight, the gradients with respect to the localization output is multiplied by the ratio between average LRP loss and its localization component averaged over the last epoch. As a result, the localization branch also has similar total gradient magnitudes, and the imbalance between the tasks is alleviated. Compared to average precision loss, using only a rank-based localization with a naive average LRP loss yields 1.4 average precision improvement. With self-balance, the improvement is more than 3 points. Average LRP loss has similar average precision 50 values, but improves average precision 90 significantly. And the correlation between classification and localization also improves. In order to increase the mod performance and decrease training time, using generalized intersection over union and adaptive training sample selection contribute around 5 points improvement over AP loss. Comparing self-balancing mechanism with constant weighting shows that self-balance without any additional hyperparameter yields similar performance with constant weighting, which ends up with different scalars for IOU and GIOU. To empirically validate the theorem that identity update guarantees balanced training, the total gradient magnitudes of average LRP loss is compared with focal loss and cross-entropy loss. On the left, the rate of the total gradient magnitudes of positives and negatives for these loss functions is shown, and on the right, you can see the loss values during training. While average LRP loss exhibits perfect balance between the gradients throughout the training, the derivatives of focal loss have large fluctuations, which biases training towards positives or negatives alternately across iterations. As expected, imbalance impacts cross-entropy more, as it quickly drops overfitting in favor of negatives, since it is dominated by the error and the gradients of this large number of negatives. In the last part of the talk, I will present rank and sort loss, RS loss in short. Different from average LRP loss, RS loss is also shown to be used on instance segmentation, which requires the objects to be localized in pixel level by masks and classified properly. Previously proposed ranking-based loss functions, average precision loss and average LRP loss, offer two important advantages. They reduce the number of hyperparameters by directly optimizing performance measures, and they are robust to class imbalance due to their ranking-based error definition. On the other hand, they need longer training with more augmentation, and they do not consider correlation by explicitly modeling positive-to-positive interactions in the classifier, which have been found useful in the literature. For example, while average LRP loss yields better results than the cross-entropy and GIOU loss combination once it is trained longer, it performs on par using the 12 epoch training setting. Also, average LRP loss performs significantly worse after the first training epoch. These are because the epoch-based self-balancing mechanism of average LRP loss tends to converge better when the model is trained for longer epochs. Secondly, the classification target of average LRP loss is not designed properly to promote correlation. One common method to promote the correlation between the classification and localization during training is to employ an auxiliary head, which aims to regress the localization qualities of positive examples. Then, during test time, the outputs of the classifier and auxiliary network are combined in order to have a joint score. The auxiliary network is supervised by an additional loss component, which is in general cross-entropy loss, since the cross-entropy loss can be employed when the target values are between 0 and 1, as in the case of IOU. On the other hand, in this setting, while the auxiliary head is only trained by positive examples, during test time the labels of the examples are not available, hence all the examples are propagated to this head, causing inconsistency between training and testing. Besides, an additional head implies more space and inference time as well. Lee and his colleagues removed this head and directly trained the classification network to regress the continuous IOU values of the examples. Training the classifier in such a way was challenging since while focal loss is robust to imbalance, it is not designed to handle the continuous labels. The authors replaced the coefficient of focal loss by the absolute distance between the ground truth label and the prediction to overcome this challenge and coined their approach as quality focal loss. RS loss has a similar motivation with quality focal loss, but differently, RS loss aims to leverage the benefits of ranking-based loss functions. Different from existing ranking-based loss functions, which do not consider positive-to-positive interactions according to train the classifier, RS loss aims not only to rank positives above negatives, but also to sort positives among themselves with respect to their continuous IOU values. This slide presents the relation between RS loss and LRP error. Rewriting the current average LRP error using the components of LRP error presents that the error is based on false positive and localization components of LRP. Since these two components are already optimized by the first two terms, their multiplication can simply be ignored. Note that the ignored term ensures the range of the error to be squeezed into 0 and 1, thereby requiring an epoch-based self-balance mechanism for the instability of an iteration-based self-balance mechanism. The resulting expression corresponds to the current rank and sort error, such that the first part measures the ranking error between positives and negatives, and the second part evaluates how well the positives are sorted with respect to their intersection over unions. Given logits and their continuous labels between 0 and 1, such as IOU, RS loss is defined as the average of the differences between current and target RS errors over positives following the identity update. And this part corresponds to the current RS loss. Given a batch of positive and negative examples, note that the current RS error on ith positive example considers all examples with larger logits, and it is the sum of the current ranking and sorting errors. While the current ranking error is simply the precision error, the current sorting error penalizes the positives with larger logits by the average of their inverted labels. Our target on each positive is to rank all positives above negatives, and at the same time sort positives with respect to their localization qualities. The RS error in that target ranking yields the target error. As a result, the target ranking error is always 0, but target sorting error can be non-zero. As identity update suggests, the primary terms for ranking and sorting are the products of the defined losses on a positive example and the probability mass function. The probability mass functions distribute the error uniformly over other examples, causing the error. More precisely, for positive-negative pairs, the same probability mass function for AP and average LRP losses are adopted. But differently, for positive-positive pairs, the sorting probability mass function distributes error uniformly on positives with larger logits but smaller IOUs. Considering that if there is a sorting error on a positive example, then this is caused by another positive example with larger score but smaller IOU. Similar to AP and average LRP losses, simplifying the expressions for negative and positive examples, one can obtain the updates of the loss function with respect to the logits. Note that, unlike negatives, the update for positives includes two terms in opposite directions, in order to sort the ith positive accordingly. While the first term aims to promote the example, the second term aims to demote it based on its interactions with all positives. This slide presents how rank and sort loss is used to supervise a generic visual detector. The upper part of the figure presents how kth stage of a generic detector is trained. There can be sampling heuristics to address class imbalance, followed by classification, box regression, mask prediction heads, and an optional auxiliary head. All these heads have their own loss functions, and then the loss functions of each subtask from each stage are combined by a scalar lambda as shown in the bottom of the slide. Once arrest loss is employed, due to the prioritization of positives by the classifier during training, detectors do not need an auxiliary head, and due to its ranking-based nature, arrest loss can handle imbalanced data without any sampling heuristics. Using GIO loss to train box regression head and dice loss to train mask prediction head ensure similar ranges of all losses. Then, similar to average LRP loss, task balancing coefficients are not tuned, but differently, they are set to the ratio between arrest loss and the corresponding localization loss every iteration. Finally, to consider classification output by the localization heads, GIOU and dice losses of the examples are multiplied by their confidence scores. To summarize the advantages of using arrest loss, first, it simplifies the training since no auxiliary head or sampling heuristics are employed, and it has been shown on 7 different detection and segmentation methods on 2 different datasets that one only needs to tune the learning rate. Second, it enforces correlation in both branches, thereby promoting better performance. And finally, it is applicable to a wide range of detection and segmentation methods. In terms of its contribution to the performance, using arrest loss with standard faster RCNN as a multi-stage object detector improves the performance by around 3 AP and 2 optimal LRP points on COCO dataset, outperforming existing RCNN variants. Arrest loss does not have any sampler, auxiliary head, and has the least number of hyperparameters. By using Carafe FPN instead of the standard FPN, the performance improves nearly to 41 AP. Arrest loss can also be used on one-stage object detectors, ATSS and PAA, which essentially differ in positive-negative assignment. Comparing arrest loss with focal loss, AP loss, quality focal loss, and average LRP loss with or without auxiliary heads shows that arrest loss outperforms its ranking-based counterparts and performs similar to quality focal loss with less number of hyperparameters. As an example for multi-stage instance segmentation, training the mask RCNN with arrest loss on the long-tailed Elvis dataset improves baseline by around 3.5 mask and box APs, especially the improvement for rare classes is notable, which is by around 7 AP. As a one-stage instance segmentation method, YOLACT has several training heuristics and carefully tuned loss weights. Removing each of these training heuristics has a significant impact on the performance of YOLACT. However, without these heuristics or carefully tuned weights, YOLACT improves the performance. To analyze its robustness to imbalance, faster RCNN is trained with and without random samplers on both stages using COCO dataset, and mask RCNN is trained without random sampler on the long-tailed Elvis dataset. In such a way, the imbalance between positives and negatives gradually increases with a range between 1/7 to around 1/10,000. Areslos can successfully train all these configurations without any tuning. On Coco dataset, it performs the best when more data is available after the random samplers are removed. On the other hand, when the samplers are removed, the performance of the standard cross entropy and GIO loss combination rapidly degrades. In this tutorial, we first discussed the basic ways of evaluating visual detectors, then presented an analysis of performance measures, and explained why LRP error has advantages over the existing ones. And finally, in this part, we aim to delve into how the gap between the training and evaluation can be reduced by introducing identity update and its applications to optimize average precision loss and LRP-based loss functions. We sincerely thank all the institutions that contribute to this tutorial. Thanks for your time.
Okay, with this video, we conclude the tutorial. Thank you very much for staying with us. Thank you for your time. Now we can get questions if you have any. There's a question in the chat window. Is the recording available online? We are going to make the recording available on the CVPR site, on that platform that was provided to us. And then we will also share these videos on our website of the tutorial. But there will be a period, there's a content embargo. After that, we will be able to publicly release the videos. But you can always email us if you cannot access the materials. You can contact us. Thank you. Okay, then maybe we can call it a day. Thank you very much again.
Thank you, everyone.
Thank you.
Okay, I'm ending the recording here.